Okay, so here's some notes to go over this idea of uniform acceleration or constant acceleration and how it relates to position time graphs and instantaneous velocity. So we've seen through a couple labs that objects that have uniform constant acceleration will have a position time graph that's shaped like this. It's a parabola. So it's got this curve, and the relationship between position and time is something like this. So as time goes, the relationship, it's a quadratic equation. So if you were to graph x versus t squared, you get a straight line. That's the relationship. Okay, we can find instantaneous velocities from this graph by drawing tangent lines and finding the slope of the tangent lines. So I've done that a couple places already. So for instance, at 4 seconds, if I draw this tangent line, I can get this slope. So the slope is just rise or run. So in this particular tangent line, I said that the rise of the delta x is 50 minus 10, which is 40, and the delta t was 2.4 seconds. And then I found another instantaneous velocity. This one was at 8 seconds. So there's my tangent line, and then I found the slope of that line. And you can draw, I could have drawn a tangent line that goes all the way out to here, and I could use these 2 points to find the slope. It doesn't matter because the slope is constant. So I have 2 tangent lines. I have a curve on a position time graph, and I can do some analysis with this. So first of all, we already know from previous studies that average velocity is the displacement divided by time. So we can find average velocities on this graph, and we can find instantaneous velocities. And I thought we could take a look at how those compare. So let's look at the time from, say, at 4 seconds. So at 4 seconds, we could say it's traveled some displacement. We could figure out its average velocity. So this would be equal to v average would be equal to delta x over delta t. So I think it looks to me that right at 4 seconds it's traveled 30 meters. So we'll say this is 30 meters divided by 4 seconds. So that is, trusty calculator, 30 divided by 4, 7.5 meters per second. That's the average velocity between 0 and 4 seconds. What did I say? 7.5. Okay, the instantaneous velocity, though, is the slope of the tangent line at 4 seconds. So we would say slope at 4 seconds. And that I've already have there, that's 40 meters divided by 2.4. So the instantaneous velocity is 16.7 meters per second. Or just call it 17 meters per second. Okay, so that's one. Let's do another point. We'll do the 8 seconds. So we could say that from the average velocity from 0 to 8 seconds is equal to what started at 0, position 0, and it went up to position, looks like 130. So it's 130 divided by 8. So that's 16 meters per second. That's the average velocity between 0 and 8 seconds. The instantaneous velocity, however, is the slope at 8 seconds. And I think I have here, oops, I've erased some stuff. That should be 150. So this is 50 meters. So 50 over 1.6. We'd expect this number to be bigger than the 17 because the slope is clearly larger. And there now we have a average velocity of instantaneous velocity of 31 meters per second. Oops. Okay. So there's a comparison between finding average velocities and instantaneous velocities for something that's going constant acceleration. Okay, we can do some more analysis on this. You would have done this in their lab. We can do a whole bunch of instantaneous velocities and come up with new data, and then we could plot those instantaneous velocities against time. So this is just an example graph of a velocity time graph produced from a position time graph. So you'll never get perfect data. You're always going to get some data that kind of looks like this. And you can get the equation of this line. So the equation of this line was y equals 0.0136 x times. So we could actually rewrite this in physics terms. This would be v equals 0.014 meters per second squared. Those are the units. So the slope, when you think about slope, we have meters per second. That's the y-axis, and the x-axis is time, which is seconds. So it's meters per second, or meters per second squared. So that's the slope times time plus some initial velocity, which was 0.14 meters per second. So that's the mathematical model for this particular graph. So we could take like the equation of the line and get it into like a nice mathematical model. Okay, so the slope of this line is the acceleration. It's how fast the velocity is speeding up. So because this is a positive slope, it's accelerating upwards. If it was a negative slope, you'd say it was accelerating downwards. And now that you consider this graph here, we can say that we have 4 different representations for modeling constant acceleration. So we have position diagrams like this one. So that's one model or representation. We have velocity time graphs like this. So that also represents constant acceleration. We can do motion maps. So a motion map for this kind of thing would be something like this, where the spacing between the change in position between each second is going to get bigger and bigger and bigger. So that would be the motion map. Put little arrows in there. The arrows essentially represent the velocity. So you'll see larger arrows. And then we have a mathematical model. This is a general model that applies to this thing. This is a specific model. The reason why I'd call it specific is because this model relates to only this particular graph because it has a very specific acceleration, a specific starting velocity. So we could generalize it by saying, well, for any kind of motion, we have a velocity which is equal to the slope, which is acceleration, times time, plus the initial velocity. And usually we write it around we usually put this thing first, but it doesn't really matter. So that's a general mathematical model that applies for constant acceleration. And the last thing that we've looked at in labs as well is that we can get a lot of information from this velocity time graph. From this velocity time graph, we can get the slope, which is acceleration. We can get the initial velocity. We can get the final velocity. We can get any velocity. Like at 2 seconds, we could say the velocity is 0.4 meters per second. Or at 6 seconds, the velocity looks to be like 0.96 meters per second. And we could also get the displacement from this graph. And the displacement is the area between the line and the horizontal axis. So I'll just redraw this here. Here is the here's the graph. So this is 0, this is 0. That is, I think it's 8, right? 8. And this point there was, I think we said it was 0.014. 0.014. And the final velocity was, looks to be like, at 8 seconds is, looks to be 0.12, I don't know, 0.123. That's my estimation. 0.123. So here's that velocity time graph resketched. The area between the graph, the line, and the x-axis is that area there. We can calculate that area. this total area is equal to, well, this is a rectangle, so that's easy to calculate. That's 0.014 times 8. And then we have a triangle here, so we'll calculate that area. So the triangle is the height times base times 1/2. So it's 1/2. The height would be 0.123 minus 0.014, and then the base is 8. So we can get that area. Oops. So let's put that in the calculator. 0.014, oops, times 8. And then that's that part. And then we have 0.123, 0.014, subtract that, times it by 8, divided by 2. You get 0.55 meters. So that's finding displacement from a velocity time graph. So that's an overview of kind of where we're at now that we have 4 representations of constant acceleration.